Okay, let's go to start up there. Hopefully took the weekend to get live back here for spectroscopy. And today we're going to get into proton NMR a little bit more and see if we can get more solidified on the subject. Okay. So, take a look at this molecule here from your book. Kind of a bigger molecule there. Let's go through our analysis. What's the first question we should ask of ourselves? The number of peaks. Okay? How many peaks do you think this one here gives? Any planes of symmetry? Okay. So here you're going to get a peak for those, and anytime you have this big T-butyl group, okay, you want to write it down. That makes all those hydrogens the same, okay, or what we call equivalent. Okay. Sometimes you see a big T-butyl group. All those will be the same. Okay? So suppose we wanted to draw the NMR for this. Okay? What would be the most downfield peak, do you think? What is the Deshielder? No, the C double bond O, the carbonyl. Okay, so this whole thing is the Deshielder. Well, what's the closest to it? A and B. Okay, so we got two things equal distant, right? So how do you determine? Write it down. The carbon with the fewer hydrogens will be more downfield. Okay, the fewer hydrogens. So CH2s would always be more downfield than the CH3. Okay, so B will be most downfield, and then A, and then C. Okay, so we just conquered two things there. One was what? The number of peaks. And then two, we conquered the peak position. Or sometimes that's called what? The chemical shift. Very good. Lastly, we do what? The peak splitting. Okay. All these peaks will look like what? Doublet? Triplet? They will all be what?
Triplets.
Okay. What's the neighbor for this one? Any hydrogens there?
No.
But here, no. Here, no. So what will these all be? Singlets. Okay. So B, A, a little taller. Then C would be a nice big peak. Why is C so big? How many is it representing? 9 hydrogens. And A, 3 hydrogens. And B, 2 hydrogens. What were those called? Those hydrogen counts. What do we call them? The integration. The integration. Okay. So there By drawing this and labeling and so on, you have fully demonstrated knowledge of the NMR of this molecule. You have it fully under your command, under full control. Okay? So expect to see a problem like this on your quiz this week in your study sessions. Okay? Any questions on this one? Anything at all? You look at the hydrogens next door, there's no hydrogens. Remember we went through the N rule. What did N stand for? What did N stand for? Don't tell it.
I wasn't here.
Then tell it. That's what happens when you miss. Okay? And the N's no more for neighbor. It stands for what? Negative. Because you missed class. Okay, so turn that negative into a positive. Okay. So let's tackle something a little different here. Let's look at this molecule. Okay, a nice simple one, ethanol. How many signals will this one give? How many different hydrogens are in there? Okay, why'd you say two? One, two, then that one, the OH. So here we're exposed to the OH hydrogen. Okay, so we can label these A, B, and C. Remember, if I see a hydrogen, it's got to show up. Doesn't matter if it's on an oxygen or a carbon or something else, it's going to show up. Okay, and there's no mirror plane in there, so all three of these will be different. Okay. Which one will be most downfield? C, because that's right on the oxygen. See that? That's right on the deshielder. Okay. So what would this spectrum look like? Let's draw our graph here. And C is most downfield, then B, then A. Okay. So now, what will the splitting look like? Let's do A first. What will A look like?
Triplet.
Triplet. Okay, because next door are two hydrogens. What will B look like? Need to give you some help. Need to give you some help. Okay, you can write it down. OH hydrogens will not split CH hydrogens. OH hydrogens will not split CH hydrogens. Okay? So what will B look like? It'll just be split by those to the quartet. Okay? So there's no splitting going on between those. Okay, the oxygen kind of blocks it away. So what will C look like then, do you think? A single. Okay, a little tiny one representing one hydrogen. Okay. Any questions on this one? I want to introduce you to the alcohols because you'll see those so that you know that the OH is not involved in the splitting. It's kind of an island all to itself. Okay. Any questions on the alcohols? Okay, so today I wanted to introduce you to some new Deshielders, okay, besides these electronegative atoms, okay? Let's look at these new Deshielders right here. What we're going to look at are double bonds, that these can act as Deshielders. Okay? In particular, part of the double bond will be the pi electrons. Okay? But we'll just say double bonds because pi electrons are part of the double bond. Okay? So these things can act as Deshielders. So let's take a look. If I had a carbon-carbon double bond, okay, that thing can act as a Deshielder. Okay, so let's see what's going on. Suppose I had some hydrogens out here. Okay. And let's suppose that we put this thing in the NMR. So what's the first thing it's going to feel? What's going to be blasting it? The magnetic field. So B applied is going to nail it. Okay? So this B applied, what it's going to do, as it does in all molecules, it is going to apply stress to the molecule. Okay? So if it applies stress to the molecule, what happens is these pi electrons in the double bond, they start circulating. 15 minutes later. These pi electrons start circulating. Okay? And they circulate because if, remember, a charged particle starts circulating like an electron, it can generate a magnetic field. Remember, if you take a coil around a battery, that can turn into a magnet. Same thing here, this starts circulating, and so it'll generate a magnetic field against the applied magnetic field. Okay? And that's what we call B induced. Okay? So it's induced by the applied magnetic field. Okay? So it's fighting against that stress to try to quench it, to try to knock it out. Well, this magnetic field line loops all the way back around like this. Okay? And it does the same thing on the other side. Okay? So that's the power of those pi electrons. They're mobile enough to be able to circulate to generate that induced magnetic field. Okay? Well, when it does that, okay, just shut the door, please. Okay. Okay. So this magnetic field comes around like that. Okay. This applied is going like that. Look out here, these arrows are going with this arrow here. Okay? So that these electrons will what? will they feel the magnetic field easier or more difficult? Since this is going with that, it'll feel it easier. And so that will cause those electrons to show up where? More downfield. More downfield, okay? So these magnetic field lines end up deshielding anything attached to those carbons out there. Okay? So you got extra deshielding occurring there. If I had something in here where these lines were going against the magnetic field, what do you think would happen there? If I had something in here, that would strongly shield those hydrogens. If I could get a hydrogen in there, that'd be difficult to do. Okay? But that's what we would see. Okay? So these double bonds can act as deshielders. Okay? Same thing if you had a carbonyl. A carbonyl has that oxygen, so you might expect it to be even a little bit stronger deshielder than the regular carbon-carbon double bond. Well, to give you numbers, these hydrogens show up between 5 and 6 parts per million at your chemical shift. If I have a hydrogen on a carbonyl, it'll show up somewhere between 9 and 11, so a little bit more downfield. And lastly, if I had this carboxylic acid, that's a very, very deshielded hydrogen, going way downfield between 12 and 15. Okay, so if you see anything down there, it's a tip-off that you have a carboxylic acid. Anything between 9 and 11, it's a tip-off, you have an aldehyde hydrogen. Anything between 5 and 6, tip-off, you have a hydrogen on a carbon-carbon double bond. Let's look at one last one. And that is the benzene hydrogen, okay, or any aromatic hydrogen, okay. These can generate strong induced magnetic field lines, okay, that are a little bit stronger than the regular carbon-carbon double bond, okay. So where do you think a benzene hydrogen would show in relationship to 5 to 6? Would it be more downfield or a little bit more upfield than that? If this line is stronger, it'll be more downfield, okay? And it shows up between 7 to 8, okay? If you ever see a peak between 7 and 8, write it down. I can draw a benzene molecule. Okay? So those are some exposure to some extra deshielders that we haven't seen. Okay? Any questions on those? Okay. These lines that get generated that be induced, or they're sometimes called flux lines, that help to deshield those hydrogens. Okay, well, let's take our handout now. Okay. Take our handout. And let's look at the front spectrum in the middle. Okay? See if you can work on that structure. Okay? Draw any parts of it based on what you see there. Okay? I'll erase the board and we'll work on it together in a second. Okay? But just see what you can do. Just see what you can do on your own, based on what we've covered today and earlier. Okay, so throw some hints in there. How many peaks are we seeing?
4.
4. Why not 5?
Because 0 is TMS.
TMS, told you, forget about it. Okay, so never count 0 as a peak. Okay, so we have 4 signals. Okay, 1 is a little bit above 2. Looks like that's a singlet. Okay, and we have 1 just before 4, okay, at about 3.8. And then what do we have between 7 and 8? What does that look like? 2 doublets. Okay, so that's kind of a sketch of what we're looking at. Okay? So, based on this sketch, is there anything that I might be able to draw? Yeah. Okay, what did we just go over? Anything between 7 and 8, we have a benzene ring. Okay? So let's just go ahead and draw that benzene ring. Okay, if you look, it gives the molecular formula as C9H10O2. See that? So we've used 6 of the 9 carbons. Okay, so I've gotten a lot out of the way, which is nice. Okay. All right, so that's the first thing I can draw. See that IR, couldn't really tell that. NMR, oh, we got it. Okay, the next thing, I'm going to give you some help here. So anytime you see 2 doublets between 7 and 8, that tells you, write it down, that I have para substitution. That I have para substitution. Okay, so that tells me I have 2 groups on the benzene ring that are para from each other. Okay, so if I draw the hydrogens on the benzene ring, I'm going to get these here. Okay, so try to draw this in your notes however you can. When I have para substitution, that creates a mirror plane right there. See that? So that's going to make these 2 the same and these 2 the same. See that? So I can label these maybe A and B. Okay, so that's what that para substitution does. Okay. So A is what? Being split by B into a what? To a what? What are they? A doublet. And B is being split by A into a A doublet, okay? So these two doublets are representing what? 2 hydrogens each, okay? So I've conquered that part of the NMR. I have it under my control. I have it under command, okay? Now I have to figure out these 2 things. Give me some help. I don't know what's going on. What does, if I have 2 singlets here, what information can you tell me about it? Anything? No. No neighboring hydrogen. Very good. No neighboring hydrogen. Does not tell you have an OH. Okay? It could be an OH, possibly, but doesn't guarantee it. It just tells me I have something next to something else with no hydrogen. Okay? Or it could be something next to an OH. I don't know. What could I do with IR to get confirmation about that? What would IR tell me to give me some major help here? I have oxygen in the molecule. So that tells me I have maybe an OH, or I could have a carbonyl. What would IR do to tell me? IR would tell me real quick, wouldn't I? If I had a carbonyl, I would see something at 1700. If I had an OH, I'd see that broad stretch at 3500. Okay? Well, this didn't give us here, but I'll give it to you. You would see a nice stretch at 1700. Okay? So we have a carbonyl. So let me give you the rest of the molecule here. Okay. So we have 2 CH3s next to no neighbors, singlet, and this next to a 0 neighbor singlet. Okay? So I could label these maybe C and D. Okay? Which of these 2, let's start with C. Which of these 2 do you think C will be? It'll be the one near 2. And D will be more downfield. Why is D more downfield? Because I'm on a strong deshielder. I'm not only right on the oxygen, but it's feeling that carbonyl. Remember the acid hydrogen, if this was an H, would be way down here at 15. Well, I got a CH3, so it's not taking me down to 15, but it's going to take me down a good chunk. Okay. The other one, C, CH3s usually like to show up at around 1 or under. But why is this C being pulled down? Because of the benzene ring. Okay, so the benzene ring is pulling it down. See, it's not right on the benzene ring like these hydrogens, which are showing up 7 to 8. So if I'm on a carbon, it'll pull me down a little bit. Okay? And so those are showing up at a little bit higher than 2. Okay? So I'm not asking you to give me exact peak position, is it at 2.1 or whatever, but you should be able to give me relative peak position. That D was more downfield than C. Okay? Any questions on this one? The main thing I wanted you to see was benzene hydrogens in the para substitution. That's a signature pattern. A signature pattern. Okay? So let's try some more here. Okay, if you go to the back of the page. Okay, why don't you try the one at the top of the page? Okay, I'll give you a couple minutes. This one up here. Okay, look at the molecular formula, then go through your 3 rules. Okay, so I redrew it up here, make sure you're seeing that those are doublets. That's it, you got a doublet and a triplet down here. This is a big singlet. Okay. So you can see the NMR lines aren't as crisp like we draw, so just to help you there. So we have 3 signals, so 3 hydrogen types. Okay, so you should have seen that. Again, that should be easy by now. The things, just write it down. That's good data. Okay? What's one thing I could immediately draw? Benzene, okay, between 7 and 8. So let's tackle that. What is that integration telling me on 7? What's the integration telling me? Look at the sheet. No. What is the integration telling me? I got 5 hydrogens. Okay? So that signal around 7 is representing these 5 hydrogens. Okay? So sometimes you can get a singlet in the aromatic region, and that's telling me I got 5 hydrogens, so I just have mono substitution here. I just have 1 group on the benzene. Okay? Some of you were trying to do 2 groups. No, you didn't see 2 doublets, did you? Okay. What else do I see from here? What's that? An aldehyde group. There's an aldehyde hydrogen. Okay? So I could maybe just draw that like that. Just draw a piece. Okay? And that's being split into what? A triplet, so that must be next to a CH2. See how that works? And that CH2 is being split into a What is that?
Doublet.
Doublet, so it's being split by that.
Yeah.
Okay, so I can just go ahead and connect that right there. End of the problem. Question?
Do we have to connect it in a certain spot, in this case right here?
What do you mean? Yeah, it's connected right to the benzene. I could have connected it to,
Right, that's all right.
yeah, okay. Okay, so let's label A, B, and C. Okay, so A is here, C, and then all of these are my B hydrogens. Okay. Any questions on that one? Okay. All right, let's try another one. Go down and do the next one in the middle. Okay, this one here. I'll give you a hint on this one. The IR shows a major band at 1,700. There's nothing at 3,500. Somebody have the sign-in sheet? Ashley here?
Me?
Oh, see me. Okay, so let's tackle this one. I have 3 signals. I have a triplet, a singlet, and a quartet. Okay? Now let's just work on what the splitting tells me, pieces that I have. what piece does this tell me I have? CH2, so I'll just write it down. What piece does this thing tell me I have? CH3, so I bet that CH3 and the CH2 are next to each other. They're splitting each other. See that? That's a good signature pattern once again. If I see a triplet and a quartet, you can pretty much take it to the bank that they're splitting each other. Okay? That's the signature of what? An ethyl group. Okay? So, I still have that singlet to work with. And let's finish the molecule here. Okay, remember I told you only had carbonyl, there was no OH. So this makes the CH3 a singlet because its neighbor has no hydrogen. Okay,
I have a question.
question?
Now, it says that there's camera.
Okay. So why is A compared to C, why is C more downfield than A? It's right next to the deshielder. A is further away from it. Okay, so that makes sense.
Can you just know that it's 2C double bond O because it has to?
Yeah, you didn't really know that. Kind of had to work that out a little bit. Okay. If you didn't get that, that's okay. As long as you wrote down one carbonyl. Okay. But it kind of has to be that in order to get the other singlet. Okay. There's no other way to arrange things to get a singlet without that. So just give this to you. I know that was maybe hard. Did anybody get that structure? Okay, that's okay. As long as you got pieces of it there, that's what I want at this point, okay? As you keep working these things and practicing these things, jump on these things after today. You have a quiz this week on these things, okay? So make sure you're ready for that.
I had to do the same thing, Badger, it is a line structure. If we're drawing like on the quiz, can we do lines instead of the?
That's fine. Just make sure you label correctly. Okay? All right, so let's call it there for today, and we'll come back to this on Wednesday. Yeah.